In this video, we're going to identify and discuss the features of external flow. So the first thing that we need to answer is that what is external flow? Well, any situation where the object is completely surrounded by a fluid is termed as an external flow. And then there's different types of external flows too. Um, there could be flows of the form of that would involve air, let's say. It could be aerodynamics. So that's one type of external flow. And when we talk about aerodynamics, we are basically talking about flows around an object like an airplane, let's say. So airplane flying through an atmosphere, that would be an aerodynamic flow. But there's other types of external flow that are important too. For example, even surface vehicles. That's another type. By surface vehicles, I mean cars, trucks, bicycles. And if it's actually become a very important topic, not just recently, but in terms of trying to design and improve vehicles, not just in terms of how they look aesthetically, but also because of how they function in terms of more efficient fuel consumption, let's say, um, or maybe improving the handling characteristics of the vehicle. So it's important to design these cars and trucks and vehicles by analyzing how the fluid is flowing across these cars. That would be the fluid would be air, right? So if you've got a car, let's say, um, the fluid that is going to be flowing across it is going to be air. So the object is the car, and there can be any kinds of objects here. And the fluid is obviously air. So this is another kind of external flow. Then, other than surface vehicles, you could also talk about ships. So those would be then surface vessels or submerged vessels too. So that's another type here. You could talk about submarines, you could talk about ships. So then the analysis becomes a bit more complex because now you're talking about flow across these ships by not just air but also water as well. So now the object is surrounded by two fluids, right? Or it could be surrounded by just one fluid, which would be water if you're talking about submerged vessels. And then, other than this, we also have types of external flows where the objects are not completely surrounded by fluids, but they're in some kind of external flow situation. Like, for example, it could be a building, and especially when we're designing high-rise buildings, skyscrapers, we need to be careful about the wind effects then and how that would interact with the building. So that is another kind of external flow that is possible. And so, although there's so many different types of external flows that exist, at the same time, there's different approaches that exist as well in terms of how to solve um, or how to obtain information that would be related to the fluid forces that are being developed by external flows. So first of all, we would have, let's say, the theoretical approach. That is the first approach. And then we could have a completely numerical approach to solving the governing equations. Or we could have the experimental approach. So these three approaches we could use to solve for the external flow governing equations. But the thing is that with the theoretical analysis, when we're talking about analytical equations, um, the governing equations become a bit too complex because not only um, is a different kind of geometry involved, and these geometries then can be very complex, but also the amount of information that is then that we need to account for in terms of the variables, pressure drop, let's say, or in terms of velocity, and in terms of all of these kinds of variables, all this information, it becomes a lot more complex to solve the governing equations then. So we need to then obviously move towards computer solutions. But before we do that, we could just go on to scaled models, or we could just use prototypes, let's say, and we could carry out experiments. So if we are talking about experiments, the first thing that could come to your mind is wind tunnels, right? So obviously testing can be done through wind tunnels. We can test model airplanes, we can test buildings, we can test any kinds of objects placed within the external flow in a wind tunnel, right? So for example here, this is just an example for you to see how this vehicle is actually, this car is being tested in a wind tunnel. And if we want to achieve a better performance of our cars or bicycles or other objects, let's say, it has to be done by analyzing the flow across these objects in wind tunnels, right? But this is an expensive approach then. And now, because of the advancement in different techniques based on computational fluid dynamics, which is CFD, so we can apply the numerical methods based on CFD-based numerical methods that would be capable of then predicting external flows past any kinds of objects. So here's an example. This is a simulation, and this is just a still of that simulation that shows streamlines, let's say, around the Formula car here. And this is being predicted by CFD. And it would be comparable to the experimental approach if you would like. So CFD techniques do exist, although analytical solutions don't really exist for a lot of cases. But at the same time, we can benchmark different simple cases, and based on those benchmarking techniques, we can go ahead and compare more complex cases and find out, let's say, what the external flow is going to look like for this car or any other kind of objects. So in this video, we're also going to be talking about the characteristics of external flow past different kinds of objects. We're going to be looking at streamlined objects. We're going to be looking at blunt body objects. We're going to see what that means. But first, we need to look at just the general characteristics of external flow. And when I say general characteristics of external flow, then obviously there's different terminologies that we need to be aware of. So any body that is being immersed, let's say, in a moving fluid, let's say air is flowing around that body or water is flowing around that body, it would experience a resultant force because of the interaction between the body and the fluid, right? So in some instances, the fluid far away from the body would be stationary, and the body would be moving through the fluid with a velocity, whatever that velocity may be. And in other instances, then the body is stationary and the fluid is moving past it. So, for example, an instance where the fluid far away from the body is stationary would be, for example, an airplane that is flying through the air. So, relatively, air is stationary because the airplane is flying at a much higher speed, a much higher velocity. So that's why that's one instance. Then in another instance, it's possible that we have a building now that is stationary, and then wind is blowing past that building. So that is the case where the body is stationary now and the fluid is moving past the body with a certain velocity. So in any of these cases, we can fix the coordinate system in the body, and we can treat the situation such that the fluid is flowing past the stationary body with a certain velocity. And that velocity is something that we represent by U, capital U. and this is called the upstream velocity. Okay. So let me just write this down. Capital U, it indicates upstream velocity. And upstream velocity of what? Upstream velocity of the fluid, because we're treating the object as stationary. Whether it is or not, that's another story. But we can treat it in a way where the objects are considered stationary and the fluid is considered as a moving fluid. So for the purpose of this video and the subsequent videos that will follow, we're just going to assume that the upstream velocity is constant, not just in time but in location too. So we have a uniform constant velocity fluid that is flowing past the object. In actual situations though, that's not true, but we're just going to be taking this assumption and working with it for our videos. Other than this, so we could ask that what does or what would the external flow look like, and how can we describe that flow, and how can we analyze that flow? So the answer to that is dependent on different conditions. So because the structure of the external flow and how the flow can be described and analyzed doesn't only depend on what the fluid is, let's say. It also depends on the nature of the object that is present within the flow. So we categorize that in terms of three different ways. We have three general categories of bodies. The first is a two-dimensional object. So for a two-dimensional object, what we consider is that basically this object is infinitely long. It has a constant cross-section, so a constant cross-sectional size and shape. The second way we look at it is, the second category is when we've got axisymmetric bodies. So axisymmetric bodies are the ones for which we can basically cut them in half and we can treat this as a symmetry. So we consider that the object, the way it is over here, it's the same way over here as well. So instead of having to analyze this entire object, let's say, I can analyze just this half of it, and because I'm applying the condition of axisymmetry here, then what that means is that if I analyze only half of this object, the exact same behavior would be true for the other half as well, right? So how does this help us? This helps us if we are performing, let's say, computational simulations. It saves us a lot of computational time because we're only analyzing just half of the body, and we're just basically mirroring those results onto the other side as well. So these axisymmetric bodies, they're formed by basically rotating their cross-sectional shape about the axis of symmetry. So this is the axis of symmetry here. And then the third one is where we can't basically analyze the objects either as the two-dimensional object or as an axisymmetric body. So then we have to analyze them as three-dimensional bodies. Okay, so we've got, this is a three-dimensional body. This is an axisymmetric body, and this is a 2D. So we've got three different categories, and then with the three-dimensional bodies, they could or could not have an axis of symmetry, okay, or a plane of symmetry. So also one more point about the 2D bodies here, and obviously when we look at it practically, there are, you could say, no truly two-dimensional bodies because no body can be infinite, right? No real life body can be infinite. So, but there's a lot of instances where, let's say, the thickness of the body as compared to the length of it, then the length could be considered as infinite because because the thickness is negligibly smaller as compared to the length of it. So these are three different categories based on which we categorize different kinds of bodies for an external flow. Another type of classification for a body shape can be made based on whether the bodies are streamlined. So this is one of the classifications, and then the second way to classify is if we consider whether the bodies are streamlined or they are blunt. So streamlined and blunt bodies. Okay. So then what are streamlined bodies? Streamlined bodies are the kind of bodies that have very little effect on the surrounding fluids, like, let's say, airfoils or racing cars, because obviously we want to have as less friction, you could say, let's call it friction for now, as less friction as possible for racing cars, right? So then those bodies have to be very extremely streamlined. Other than that, our usual cars as well, they are usually streamlined. Now, blunt bodies, on the other hand, are the ones that have a much larger effect on the fluid. So, for example, the buildings, because the building is, just straight up right against the fluid flow, whereas the streamlined body is going to try and deflect this flow up above or below. So that's why this is called streamlined, and the blunt body object has a direct impact on the fluid around it. So these are two different categories of it, and now we're going to be looking at two major concepts when we talk about external flows. And these concepts are given the names of lift and drag. So let's just ignore these equations for a minute, and let me just move on to showing you how the force interaction is taking place when any body is moving through a fluid, and how the interaction is taking place between the body and the fluid. And now at the fluid and body interface, what are the forces that can describe basically what is happening between the fluid and the body, so at the fluid body interface. These forces can first of all be described in terms of stresses, of course, or so, and then these stresses could be of two different types. We could have, let's say, normal stresses that are because of the pressure, which is P, or we could have the wall shear stresses, right, on the body. So this tau W here shows the wall shear stress. And this is because of the viscous effects. So we've got normal stresses because of the pressure and wall stresses due to the viscous effects. And now both of these, obviously, pressure P and tau W, wall shear stress, both of these vary in magnitude and direction along the surface. So these are two important kinds of stresses that are being applied on, say, any body. Right now we're looking at an airfoil shaped body here, but this could be any object in here. So usually we would have to find out a detailed distribution of what the shear stress looks like over the surface of the body and what the pressure looks like over the surface of the body. But the important thing to remember here is that usually it's very, very difficult to obtain that kind of information. And so instead of doing or working with that, what we do is we talk about resultant forces instead. So the resultant forces then, if we are making the resultant forces out of the normal stresses and the shear stresses, the resultant force that would be in the direction of the upstream velocity, that is basically termed as the drag force. That is being represented by D here. And then the resultant force that is normal or perpendicular to the upstream velocity, that is termed as lift. Okay, so these two are basically the resultant forces based on the normal and the shear stresses. And now if I was to, let's say, look at this same body in this figure, where this indicates the body, right? Or this indicates actually a small area element on that body. So we're talking about dA here, a small area element. And if I was to, let's say, find out the resultant of the shear stress and pressure distribution here, then obviously the pressure distribution, the pressure force is going to be a normal stress, so it's being applied onto the body, whereas tau W is the shear force, so it's going to be basically along the body, right? So the resultant of both of these I can identify if I was looking at it in terms of, let's say, the forces in x direction and forces in y direction, so x and y components of the fluid forces on the area element dA. So that would be in terms of obviously the force that is being applied here, which is pressure into area, and obviously the cosine component of it, plus the force that is being applied because of the shear stress, so tau W into dA, into the sine component of theta here. And then the same way for the y component of the forces, I could do the exact same thing and apply the force balance onto it. And so if I was to try and find out the net x and y components of forces, then to find out the net components, I would have to take an integral of the forces in x direction, right? So when I'm integrating all of the forces in x direction, then that integral is going to be going to give me the drag force, right? And if I was to expand this further, then I would have to apply the integral onto basically p cos theta into dA integral over it plus tau W sine theta dA and integral along that too. And now if I was to sum all the forces in the y direction, so then I would have to apply the integral over the forces in y direction, then that would give me the lift force now, right? So because obviously y direction forces in this direction and x direction forces are in this direction, so if I sum all those forces in x direction, they would be giving me the drag force. Sum all the forces in the y direction would be giving me the lift force. Now, this is difficult to accomplish, integrating all of this, because, well, first of all, we should know the body shape, obviously, because theta is a function of the location along the body, and then we need to obviously know the distribution of tau W and the pressure force here as well along the surface, and all of this is extremely difficult to do, whether we're trying to do it experimentally or if we're trying to do it theoretically. So this is a lot harder to do, right? It's also harder to do this because, let's say, whatever the body is that here that we're analyzing. Um, for that body, theta over here is not going to be 0, and it's not going to be 90 degrees along the entire body as well. So theta is changing as we look at the location on the body. So theta would be something different here, something different over here, and theta is going to keep on changing all across the surface of the body, right? So then that makes it a lot harder for us to find out the shear stress and pressure force um, components and their distributions. The only exception to this is if we're looking at a flat plate. So if we were looking at a flat plate that would be aligned, let's say, parallel to the upstream flow, then theta would be 90 degrees along it. And if it was aligned normal to the upstream flow, that is perpendicular to the upstream flow, then theta would be equal to 0 along that flat plate. So I'm just going to leave a question here related to the flat plate now. And you could work this out yourself, maybe try doing it in SI units. So you could go through it, and you've got two cases here. The first is where the plate is parallel to the upstream flow, right? And for this, theta is going to be equal to 90 degrees. And then the second is that it is perpendicular to the upstream flow. So for this, theta would be equal to 0. And you have to find out the lift and the drag on the plate by using the equations that we just saw. So I'm just going to leave this up to you, and I'm going to move on to trying to assess how we can find out lift and drag for any object. So, like I said, that the equations that we just previously looked at in terms of drag and lift, using these equations is extremely difficult unless we were using it for a flat plate. So, but any kind of body, if we were to use these equations, it would be extremely difficult. So instead of trying to find out the details of the shear stress and pressure distribution in the body, we use an alternative approach in terms of trying to assess drag in its dimensionless form and lift in its dimensionless form as well. And the dimensionless form of lift and drag, basically we can use those to determine the approximate values by maybe using a numerical technique, by maybe doing experimentation for it. So the dimensionless form of lift is called the lift coefficient, okay, and it's represented by CL here. It's capital C subscript L. This is called lift coefficient, and then the dimensionless form of drag is called CD, capital C subscript D, and this is called the drag coefficient. And these are just the dimensionless forms of lift and drag, okay? It's nothing complicated, it's just the dimensionless form of lift and drag. And one important thing that we need to consider here is the area over here. And because the area is the characteristic area of the object, usually it's taken as the frontal area. And by frontal area, what I mean is that if we're looking at the object from the direction that is parallel to the upstream velocity. So if I was looking at the flow from this direction, then the area would be diameter multiplied by length, right? I mean, that is because this is a cylinder and I'm looking at this side of it. So yeah, that's going to be the frontal area over here. But it's not always the case that we take the frontal area as the area. In some other situations, we also take the planform area, which is represented by basically the if you were looking at the object from the top view, basically. So if you're looking at this, let's say, airfoil here from the top, then that would be called planform view. And then that would be equal to basically thickness into the length of it. Sorry, the width into the length of it. So that would be CL, right? and the frontal area is going to be equal to, for this one, it's going to be equal to the thickness of the body multiplied by the length of it, because I'm looking at it from this direction, right? This is the platform area, this is the frontal area. So it depends on what kind of body we're looking at, what kind of situation we're looking at, and depending on that, we would have to decide what is the area that we're considering. But obviously, the characteristic area, whatever we're using whatever we're using to define lift and drag coefficients, the area needs to be clearly and explicitly stated that this is the area we've chosen as the characteristic area for finding out the lift coefficient and the drag coefficient.